K sets the time scale. Okay, and so this first order equation typically involve one time constant, like at least in the simplest form. Okay, and there is one more observation that first order equations will involve one constant of integration. So you need to specify, for example, in here n0. That's the initial number of cells. So that's one constant you have to specify at t equals 0. Okay? So as we go to second order or third order equations, you will see for linear equations like this. Okay? I'm talking about linear equations. You will see instead of one time constant, we are going to find 2, 3, 4 time constants as we increase the order of the equation. And you need more and more initial conditions. So for second order equations, like when you are solving Newton's second law, typically what type of initial conditions do you use? Initial velocity and initial position, correct? So that means you need two boundary initial conditions. So if you go to a third order linear equation, then you will see you need 3. So initial position, velocity, and initial acceleration, or equivalent of that, equivalent of initial acceleration. And similarly, you will have 3 time constants in the problem. You will not have a simple one time constant decay. So let me take a break for 5 minutes and to start the second order equation. If any of you did not get the handout, please take it. It's here. Yeah.
I got confused on.
Can you talk to me after the lecture?
Okay.
Is that okay?
Well, the thing is, I have class right afterwards, so it was just a quick question.
Okay.
On just if anybody is attached to the sheet, I guess nobody's attached to the sheet.
So what's your concern?
My concern was that in the problem you said something about.
Some of you are using the forum. Who are using forum? Isn't it nice? And I also saw some people are exchanging emails on chat site. So use those if you have concerns and exchange ideas among yourself. So general nth order linear ODE will look like this. And do you remember, or do you know what's the homogeneous part of an equation, or whether the equation is non-homogeneous?
Whether f of t is 0 or not 0?
Yeah. So if the right-hand side is 0, the equation is homogeneous. If the right-hand side is non-zero, like ft, it's a non-homogeneous equation. And when you solve the equation, you cannot solve it all together. You need to first do the homogeneous part first, and then solve the non-homogeneous equation.
So the x's and y's all be one?
All x, yeah. That's right. And also, you might wonder why there is no coefficient here. Yeah, you can just divide it through. So you really don't need any constant here. You can just divide it through. Okay, so that's kind of the most general form of the equation you can write. And in terms of solution, you need to solve the homogeneous part first. Okay. Now, one idea you often follow in solving things in different fields, and of course in math all the times, that when you don't know how to solve, how to approach a problem, you try to write the problem in a way which you know how to solve. Okay? So you don't know how to solve nth order linear ODE like that. But do you know how to solve linear equations like polynomial equations? So you know, for example, ax squared plus bx plus c equals 0. Or you know how to solve a x cubed plus bx squared plus cx plus d equals 0. So this is the second order polynomial equation. This is the third order polynomial equation. So you know how to solve such algebraic equations. And your goal will be, can you write down this nth order linear ODE or do some transformation and you end up with such a thing. Okay? And you will see the same strategy when you solve partial differential equation. We are going to reduce the PDEs into a set of ODEs, which we are right now discussing. Okay? So when we solve PDEs, we transform them into set of ODEs. And here the idea is we have an nth order differential equation, ordinary equation, and we want to transform them into an algebraic equation. And the trick to do that is to assume a trial solution. And the trial solution you assume is of this form. And why this form? Why this particular form? Why not something else? Like what could be one motivation at least of choosing such a form?
If the derivative is the same as the...
So when you are solving first order linear ODE, what solution do you get? You get an exponential solution. Okay? So then your first guess will be, why not try the same exponential form? Okay? Because it worked for the first order. First order you know. Okay? So that's another strategy you often use. Like you try to solve it in the simplest form, say in one dimension. When I was giving you the random walk problem, I asked you to solve random walk on one-dimensional lattice or on a line, rather than first doing it in a cubic box. Okay? So the idea is if you can do the simulation on a line, you'll be able to generalize it to 3 dimension. There are difficulties involved as you increase the dimension, but so here again, similar idea. You could solve the first order, and why not try the same function? Why not try the exponential function? So if I do that, if I plug that in the equation, I get lambda to the power n d e to the power lambda t plus a n minus 1 lambda to the power n minus 1 e to the power lambda t plus a 1 lambda e to the power lambda t plus a 0 e to the power lambda t equals 0. Are you with me? So I took this solution and plugged it into the equation, in the homogeneous equation. And can you see why I got lambda to the power n in the first term? Yes? At the back? You follow? Why did I get lambda to the power n?
Because every time you do the derivative, it multiplies by lambda.
So each time you take a derivative of e to the power lambda t, lambda comes in front. So in the first term, I have n derivatives, n such derivatives. So each time I take the derivative, I have 1 lambda. So n derivatives gives me n lambdas, which is lambda to the power n. And similarly, I have lambda n minus 1 and all these things. And exponential lambda t remains as it is. So I end up with lambda to the power n minus 1 plus say 1 lambda plus a 0. Okay. And we are going to be interested mostly in second order. So, okay, let me write the general form and then we'll readily jump into the second order equation. So what can you write from this? So this is a product of two terms. One is this polynomial in lambda, which let me call f lambda, and then e to the power lambda t equals 0. Now, e to the power lambda t cannot be 0. Can it be 0? What happens if it's 0? It cannot be like it cannot be 0, and if it's 0, then the solution is a trivial solution. It's a 0 solution, which does not make sense. So the only possibility is because e to the power lambda t cannot be 0. Move to the other side. Now, if that's the case, if f lambda is 0, I have the roots or solutions of this equation. It's lambda 1, lambda 2, lambda n. And you can imagine if you plot f lambda, if you want to think geometrically, so f lambda is a polynomial function, and that crosses 0 at many times, at many points on the x-axis. This is the lambda axis, not x, but lambda axis. And these points are the roots of this equation, and those are lambda 1, lambda 2 through lambda n. Okay. So now I can write the solution. Remember, the solution is